Okay, to really understand the Bitcoin network, we need to just break it down to understand what the actual problem is that the double spend problem resolves. So, in essence, you have all these nodes or computers that are all connected to each other, spread throughout the world. Um, and they're all sharing a common ledger. So when someone's trying to do a transaction, let's say on this node, as soon as they do a transaction, they as soon as this node receives a transaction, they're going to verify it and they're going to go ahead and pass it along to their peers. Their peers all have a copy of the ledger that they have, and they go ahead and update the balance, you know. So John spent some money, updated his balance, and then he shares it to all the peers he's connected with. And they go ahead and update their balances accordingly. And on it goes. So just with this simple premise, you have a good start to a decentralized sort of payment system. But very quickly, you see a big problem comes up, and that problem is the double spend problem. And it's funny because if you look at the opening page of Satoshi's paper, that's literally what the central premise of the creation of Bitcoin solves. You can see a purely abstract, but really he says we, but we propose a solution to the double spending problem using a peer-to-peer network. And then he describes it being broken down into blocks. But by solving this double, quote unquote, double spend problem, he basically created a super solid, peer-to-peer electronic cash system. So, what is the double spend problem? Well, to put it simple, let's put it this way. Let's say you had $3,000, right? And you simultaneously went to a website that's hosted like in New York on a New York node, and you wanted to spend $2,500. And you also went to another website. Let's say you want to buy something from Sony, and you want to spend $1,000 from Tokyo. Well, if you were to do that at the exact same instant, what would happen is the node in Tokyo would verify your transaction, start passing it along, and the node in New York would do the same thing. And eventually, they're going to run into a big issue because they're going to say like, "Whoa, whoa, whoa! Hey, what's going on here? I saw that you already spent, $2,500, but you're trying to spend another $1,000. Like, I'm not going to allow that." So basically, what you have is a fracturing in the system. All the ones in Asia who saw this transaction first that was passed on from the Tokyo node, they're going to show that you have a balance of $2,000 because you had 3,000, you spent 1,000, you got 2,000 left. All the ones in Americas and let's say Europe, they're going to show you have a balance of $500. Okay, so this is very problematic now because now the network is splintered. It doesn't know. Obviously, over here, they're going to show that this transaction's invalid, and over here, they're going to show this one's invalid. So, what do you do? Well, what you do is instead of immediately processing transactions, you instead go ahead and place them in a queue. That's the mempool. And we're going to go ahead and order them, by highest fee to lowest fee. All right, and then we're going to create a block. Let's just say 1 megabyte. And we're going to take all those transactions and we're going to put them in a block. All right, so instead of doing transactions as soon as we see them, we're going to create a block. All right, and so now what we do is instead of sharing transactions, every node is hearing transactions, and they're filling up a page, a block, and then comparing them. So if we just freeze time right now and we compare it to this block here, let's say this one's at 100%, all the blocks throughout the network are all going to be a little bit different. It's probably only going to be a 99% match to the Tokyo because Tokyo is going to get some transactions in here that maybe you haven't seen yet, and it's going to build its block that way. But now the question remains, okay, so we haven't broadcast anything yet, so how do we broadcast these blocks? And what's the incentive? How do we decide who gets the first block? Are we just, drawing numbers? And what's the incentive for processing a block of transactions? Previously we got paid for each transaction that we heard first and then shared with the network, but now everyone's doing it. So how are you going to get paid for all that? So I'm going to skip over some of this because this covers the proof of work, but let's skip to the other part. All right, so all the nodes are going to do work on that block, and they're going to do 10 minutes of work. And it isn't until they've achieved doing that 10 minutes of work, that one miner can declare that they won the block. So let's say this node wins the block, all right? This is all part of proof of work. Basically, they're saying, hooray! They're telling the whole network, I won. I got the golden ticket. This is the good block. And they go ahead and put in their proof of work inside the block, and then they share it. And every other node pauses what they're doing, or probably at the same time. They verify all the transactions in your block. And they can see that you did in fact do the work, and so they say, okay, that's good, and now I'm going to pass that block along. So just with this simple explanation I've gone into, you see how the double spend problem goes away, because you're not just sharing transactions instantly. Instead, the miner in Japan would be mining your transaction in a block, the one in New York, and only one of them is going to win. Let's say the one in New York wins. He's going to win. He's going to do this whole process, and it's going to propagate over to Japan. And the one in Japan's, once this one's verified, they're going to know, oh shoot, you don't have that much money, and they're going to deny you your transaction. Now, granted, they'll probably already see the transaction because it's in the mempool, but you kind of get the gist. You sort of get rid of the double spend problem. Now, if you're still concerned, because someone could still say, you know what? It's possible that the Japanese miner and the New York miner at the same exact instant are able to mine a block. Well, don't you run into the same issue? Well, not so fast. If that were to happen, what you would essentially have is what's called a consensus fork. All right, what that means is, again, both blocks are mined at the exact same instant. So all the miners in near Japan and in Asia are recognizing this block. All the ones in the rest of the world are recognizing this block. So essentially, previously to this, the whole network had a blockchain that they were good with. But now that this scenario happened, there's a split. This is where you get the term fork. You know, one side of the world recognizes all these blocks, and then this one has the next blocks. The other one's all these blocks, and then this block. So how are you going to solve this problem? Well, it's easy. By implementing the rule of longest chain, all you have to do is wait for the next block, because statistically this isn't going to happen again in a row where two miners do it at the same exact second. On average, it should take about 10 minutes. So once the next block is mined, let's say it's from someone on this side of the world, then now you have half the world with this chain. It's one block longer. All the blocks in Asia, they saw this block, but they sort of were disregarding it because this was the one they accepted. But now that they see two blocks that are verifiable, now they're going to drop this block because this has more work. This has the longest proof of work chain. And so now you've again resolved this issue. You basically have a one block fork happening pretty much every day. This two block fork scenario that we're talking about happens about once every 2 weeks.